everyone, it's Miss Sullivan and we're talking expanding binomials. So this is just a follow on from expanding brackets and it's the fourth video for your algebra unit. Expanding binomials, before we begin, let's just have a quick little check on some language. So algebra is obviously, as we've talked about, a language that helps us think in abstraction. So what's really important about algebra is that we understand the terms that are being used. So the power in a language always comes from knowing the rules of the language and the special terms that that language uses. So if you don't know the terms, you're never going to get it. So if you don't know the language, you're never going to get it. Term being a key term of the language of algebra. So let's just have a little reminder here. When we are talking about algebra, we remember that this, when we were doing the context of index laws, that was called our base. So it could be our base, our pronumeral, or our variable. This number here is the coefficient, and we know that this is the index. Or if you're in America, it's the exponent, or the order, or the power of. So we've got 3x squared plus 7. And this, in an algebraic expression, is a constant. This can change. It's a variable. But this number stays constant. So what we're looking at here is an algebraic expression. It doesn't become an equation until I add an equal sign, so that I've got two sides that I can make equivalent. We notice that in this algebraic expression, I've got two terms. Two terms in an algebraic expression, we call it a binomial. Let's have a look at this one below. 1, 2, 3 terms. 3 terms, trinomial, anything more than 3, polynomial. Just a little reminder, when we're simplifying algebraic expressions, we're checking for like terms. Adding and subtracting, we're looking for like terms. You learn index laws first because you can apply them to multiplication and division, but remember with adding and subtracting, it's like terms. So this is not compatible with that, remembering that that is minus a to the power of 3, being careful to watch our signs at all times. A is not a like term with a cubed, which is not a like term with a times b. Excellent. But if we had something like 4a minus 2a, absolutely I can do this. 4 pencils, take away 2 pencils, I get 2a. Excellent. Just a little reminder about language before we move on. So let's move on. Expanding binomials. I do like the example that the textbook uses in terms of area with that rectangle, because I do think it's really helpful. So we know that if we're working out the area of this rectangle, we need to multiply this by this. And that this side is going to be a plus b. And we need to multiply that with c plus d. So if we have a look at this, I know that if I just bust this down, just have a little look at it this way. The area of this little one here is a times c. The area of this little box here is b times c. The area of this box up here is a times d. And the area of this box over here is b times d. So one method I could use to work this out will be to add all these up. So I could say AC plus AD plus BC plus BD. So that's the first method I could use to work this out. Or alternatively, I could say A plus B times C plus D. Again, remembering it's our convention to eliminate those little multiplication signs. So let's have a look at expanding these binomials. First, I'm going to look at the first term. So we get first term equals AC. Then I've got to multiply A by the next term, which will be positive D. It's a positive A, so we get A, D. Plus, now it's time to multiply my second term by my first term, BC, plus second and second, BD. Let's check this out. AC plus AD plus BC plus BD. As you can see, they're exactly the same. But that is probably a faster way to do it, especially when you don't have a nice, neat little diagram to guide you on your way. Again, watch your signs. When I'm multiplying and dividing, and remember we multiplied that with that, we multiplied that with that, multiplied that with that, multiplied that with that. For all of these sums, I've got to be super aware. A positive and a positive, a negative and a negative. If I've got the same sign, the answer's positive. If I've got a different sign, the answer's negative. So let's have a little look at this one. Just as our first example, x times x. We remember that x times x is just the same as saying x squared. X times negative 5 minus 5x. Let's look this way. Plus positive 3 times x, 3x, and then I've got to come across this way. 3 times negative 5. 3 times 5 is 15. But the signs are different, so the answer's negative. I've expanded, now it's time to simplify. Do I have any like terms? Yes, I've got this one. Not forgetting it's negative 5 plus 3. So I'm moving this way up the number line, and I end up on x squared minus 2x minus 15. Terrific. Just as another little one, so that this time we're looking at coefficients. So the whole point here was to remember that when I multiply x by x, I end up with x squared. Also to keep us super aware of, watching your signs. This time I want to look at what happens when I've got a coefficient. So let's have a look at this one. 2x times 3x. So 2 times 3 is 6, and x times x is x squared. Cool. 2x times positive 3. Okay, 3 times 2 plus 6x. Excellent. Let's move on to this one. Negative 3 times 3. 3 times 3 is 9, but the signs are different, so the answer's negative 9x. Then negative 3 times positive 3, so 3 times 3 is 9, but the signs are different, so the answer's negative. And again, I can simplify because I'm working with like terms. So positive 6 minus 9 takes me to negative 3x, and none of this changes. X squared, 6x squared, minus 3x, minus 9. So if I can say it for the billionth time, be super careful with your signs. All right, last thing we need to talk about. We're looking at expansion patterns. So just like we had those index laws were really like shortcuts for working with indices, expansion patterns are really like shortcuts for working with binomials. So again, I want you to have a little bit of a think about this rectangle idea, and let's come down to this one. So if I want to work out the area of this one, I know that this is a plus b, so this line here is a plus b, and I know that this line here is also a plus b. Cool. So having a look at what I did above, a plus b, this one was a plus b, c plus d, and I was trying to multiply them together. This time I'm multiplying together a plus b. And I know that when I do that, it's a plus b squared. I'm just timesing that by itself. So let's expand it quickly. A plus b times a plus b. When you see this, so note that our brackets are identical, a plus b, and they're being multiplied by each other. That's the perfect square. So a perfect square is the square of a whole number. So 2 to the power of 2 is a perfect square. Just like a plus b to the power of 2 is a perfect square. So really quickly, let's long form expand this. I know that that equals a plus b times a plus b. Brilliant. So a times a squared, a times b, ab, b times a, same as saying ab, b times b, b squared. Excellent. Let's just check that out for a second. If I wanted to work out the area of this, I would do a times a, which is a squared, then b times b. Okay, b times b down in here, b squared, but this little box here is going to be ab. I'm multiplying a by b. And this little one here is a, so a times b. ab, let's check it out. A squared plus ab, plus ab plus b squared. That's kind of cool. So when we have a look at this, I can simplify because these are obviously like terms, and I get a squared plus 2ab plus b squared. So you're allowed to use a shortcut when you're working with perfect squares. So this is the expansion pattern for perfect squares. So the shortcut is, you can remember that I'm going to square the first one, and then it is 2 lots of, so 2 lots of term 1 and term 2 plus the second term squared. First term squared plus 2 times the first term and the second term plus the second term squared. Excellent. That squared, that squared. Oh, sorry about that. I'm going to fix it up because you can't see it. So a squared at the front, b squared at the back, and in the middle, 2 times a times b. Cool. I just want to show you a little example here. Really important when we're working with a negative number. Actually, I might just squeezy it in here. If this was a minus b, so let's have a look at what that might look like. A minus b squared. I know that that's going to equal a minus b times a minus b. So what do I get here? Here I get a squared minus, so we've done this one, minus ab minus, because it's negative b times a, ab, then b times b, negative, negative. When the signs are the same, the answer's always positive, b squared. So this time, if I get, sorry, just having a little look here, I've made a mistake. A times a is a squared. Then I get negative b times a is negative ab. Sorry, positive a is negative ab. Yep, minus ab is b squared. This time it's a squared minus 2ab plus b squared. So you can notice here that my positive, a squared plus 2ab plus b squared, this is the only thing that changes. This very first sign here is the only thing that changes. So I can use my shortcut if I want. But where they're negative, I've got to remember that this first sign is going to be a negative. Okay, Having a little look here, the final thing we've got to learn about is the difference of two squares. So very similarly to this, it's basically the difference between the square of the first term, boom, A, and the square of the second term. But it doesn't happen when I've got this. It happens when I've got little non-matchies. So here's my example, little non-matchy signs. It happens when I get, oh, sorry about this, A plus B times A minus B. And let's have a look at why it's so different. So if we remember here, my shortcut, first term squared, last term squared, 2 times first term, second term. And when they were minuses, first term squared, last term squared, and it's negative 2 times the first term, the last term. Let's have a look at what happens when I expand this. A times A squared. Now, A times negative B. The signs are different, positive A, negative B, so the answer is negative. Sorry, I can't quite reach around the camera. Negative AB. Let's have a look at this one. B times A is positive AB. And then B, positive B times negative B, the signs are different, so the answer's negative B squared. But what happens here? Negative AB plus positive AB. Well, we know that from, when we look here at inverse law, B plus negative B, in this case we've got negative AB plus AB equals 0. So these two cancel each other out. And we end up with A squared minus B squared. So the difference of two squares, when I've got a positive here and a negative here, but I've got the same terms, I end up with the first term squared minus the second term squared. Terrific. All right. I'm just going to do a couple of quick little examples so that you can see the working out where I can actually reach. So let's have a look here. Expand, then simplify. So 5x plus 6 times 5x plus 6. I know here I've got exactly the same. I'm working with a perfect square. This time I'm just going to cheat and I'm going to use my little shortcut. So I know that it's the first term squared. 5x squared. They're both positive, plus 2 times 5x times 6. First term, second term, plus second term squared. So let's have a look. 5 times itself is 25, x squared, plus 2 times 5 is 10, 10 times 6 is 60x plus 36. So I just looked at the first term, squared, plus 2 times the first term, the second term, plus the second term squared. All right, this time I've also got a perfect square, but I'm looking at minuses. Really important. So let's cheat again. So let's look at the first term. It's not really cheating, it's just using a shortcut. First term squared. This time it is minus 2 times the first term times the second term, oops, and then again minus and a minus, positive 6 squared. So I get 25x squared minus 2 times 5 is 10 times 6, 60x plus 36. So as you can see, 5x plus 6 squared and 5x minus 6 squared, the only difference is that second sign. All right, let's have a little look at this one. I've got 2x plus 4 times 2x minus 4. Ooh, my little signs are different here. So I'm looking at the difference of two squares. This time I'm going to use my shortcut. I know that these middle terms end up cancelling themselves out. I'll just do it in long form quickly for you just to demonstrate that again. 2x by 2x, 2 times 2 is 4, x times x is x squared. 2x times minus 4 is negative 8x. Positive 4 times positive 2 is positive 8x. Positive 4 times negative 4, signs are different, so the answer's negative 16. So negative 8 plus 8, we know that's going to equal 0. So it cancels each other out. So let's use our shortcut. For our shortcut, all we needed to do was the square of the first term minus the square of the second term. Let's go. Square of the first term, 2x squared, minus the square of the second term. So let's see what we get. 4x squared minus 16. Sames. Okay, let's have a little look at this one. Is this one of our patterns? 2x minus 4, x minus 4. No, it's not. It is certainly not a perfect square because we're not dealing with identical terms. But just for good measure, let's expand it. 2x to the power x squared, 2x, 2 times 4. Signs are different. Negative 8x. Negative 4 times x. Negative 4x. Negative 4 times negative 4. Signs are the same, so the answer's positive. I've got like terms here. Negative 8 minus 4, moving back this way. 2x squared minus 12x plus 16. Excellent. I hope that's helpful. So it's expanding binomials, and the only two things that are really super new this year are finding expansion patterns. This idea of a perfect square and the difference of two squares. Excellent.